Hello everyone, welcome to my YouTube tutorial. In this section, I'm going to be discussing organic chemistry, and today's topic is isomers. And on the board, I have only two objectives for this section. We shall look at the definition of an isomer and then the types of isomers. So to begin with the definition of an isomer, let us first break down the word isomer. So iso and ma. The word iso means the same, and the word ma means unit. So isomers have the same unit. So isomers are compounds that have the same general formula but differ in the arrangement of their atoms. So under the types of isomers, we have what we call constitutional isomers and stereoisomers. So like we said, that isomers have the same general formula but differ in the arrangement of atoms. So with these two types of isomers, the constitutional isomers are basically isomers that have the same general formula but different arrangement of atoms. Whereas for the stereoisomers, the arrangement of atoms in space, because stereo means we can say it means something to be in space, spatial. So under stereoisomers, they are further divided into what we call conformational isomers and configuration isomers. So under conformational isomers, we shall look at what we call the carbon-to-carbon rotation isomers, that we shall see the boat and chair isomers, and also the amine inversion. So this one we shall not we shall not discuss it more in detail. Whereas the configuration isomers, these have what we call the cis and trans isomers. So now to begin with the constitutional isomers, constitutional isomers. So we said these isomers have the same general formula but different arrangement of atoms in space. For example, if I have a general formula of C2H6O, so I can have a number of isomers with this general formula. So for example, I can have CH3, CH2OH, which is ethanol. So these are 1, 2 carbons and 5, 6 hydrogens and 1 oxygen. So I can have ethanol from this, and if I also rearrange this, I can still get another group. So now this is called dimethyl ether, or you can also call it methoxy methane. So from this general formula, I have derived an alcohol and an ether. So an alcohol and ether are constitutional isomers. So another example that I can have is if I have acetone. Acetone is a ketone. So, and also I can have this is propanol. So when you look at this, they all have 1, 2, 3 carbon atoms. So that is C3, and they have 6 hydrogens, and they have 1 oxygen. So this is the same 3 carbons, 6 hydrogen, and 1 oxygen. So they have the same general formula, but they have different arrangement of atoms. So this is an aldehyde, and this is a ketone. So aldehydes and ketones are constitutional isomer. So now that you've understood what we call by constitutional isomers, so let us drop down to go to the other side and see what we mean by stereoisomers. So now, under stereoisomers, like I said, the word stereo means spatial. So these isomers differ in the way they are arranged in space. So they may have the same, they have the same general formula and the same atomic arrangement, but the way these atoms are arranged in space is really different. So under stereoisomers, we have what we call the conformers or conformational isomers, and also we have what we call the configuration isomers. So with this, I'll begin with the configuration isomers. So under this, we have what we call the cis and trans. So under the cis and trans, this type of isomers exist in what we call alkenes and cyclic compounds. So this is common in alkenes and cyclic compounds. So for example, let me begin with cyclic compounds. So if I have, for example, if I have this compound which is 4-methyl cyclohexanol. So this is 4-methyl cyclohexanol. So how do I get a cis and trans? So with cis and trans, when these compounds exist as, so this wedge, which is a bit darker, means that it is facing me, and the other one means that it is very far away from my side. So when you have this type of wedge and this other type of wedge, then you have what we call a trans isomer. So this will be trans 4-methyl cyclohexanol. But if you have two wedges, dark wedges facing you, like in this form, then this is called a cis. A cis 4-methyl cyclohexanol. So another example that we can have, we can use this other. So this is cyclobutane. So in cyclobutane, I have a methyl group and a chloro group, a chlorine atom, both with a dark wedge, meaning that it is a cis. So in cis is when both atoms are on the same side, whereas trans when the one atom is when they are on the opposite side. So this is the same as 3-methyl. So it's the same as saying 3-chloro cyclo no, this is 1-chloro 3-methyl cyclobutane. So this is the structure of that. So this is a cis isomer. Whereas for the trans isomer, when we have something like that. So this means this chloride atom is facing me, whereas the methyl group is very far away from the viewer. So now that we've seen cyclic compounds, how cyclic compounds can exist as cis and trans. So here I have an example of an alkene. So if I may draw the structure of this. So this is butene or 2-but. So this is 2-butene. So now I've drawn the cis isomer because these two hydrogens are on the same side. Remember, when you're doing confusion isomers, what makes these compounds exist as cis and trans is when the sp2 carbon, when both of the sp2 carbons have a hydrogen bonded to them. So if this sp2 carbon has a hydrogen and this sp2 carbon has a hydrogen bonded to it, then we shall have what we call cis and trans isomers. So now with this is the same structure. So the reason why these confusion isomers is defined only in arrangement of space. This double bond here you see is rigid. You cannot change it, whereas this you can rotate them around. But this bond to this carbon, the double bond is rigid. So that's why these compounds do not exist as we saw, as we shall see in the in conformers. In conformers, this bond is free, so the atoms can rotate around in any axis that they want. So under confusion isomers, these cis and trans isomers have different physical properties. So cis and trans isomers have different melting points, different boiling points. So therefore you should and different melting, boiling point, and sometimes solubility. So these conformers under cis and trans are very different from the ones we've seen, the ones we shall see under conformers. In conformers, we shall see that it's all about inversion of the carbon atom. So these conformers usually is the same molecule, but it exists in what we call in a dynamic equilibrium state. It is always converting itself from this molecule to this molecule constantly, but you cannot separate those two conformers. Whereas with confusion with confusion isomers, we can separate them because they have different physical properties. So now, if this is the cis isomer, then the trans isomer will be if I move this methyl group and this hydrogen group and I put them in opposite direction, then I will get what we call a trans isomer. So now this is a trans isomer of butene. So trans butene occurs when I change this to a methyl group and then I change this to a hydrogen group. So now these are what we call cis and trans isomers, and some of the questions that they can usually ask you about cis and trans is about their stability. So the cis isomer, the trans isomer is more stable than the cis isomer because of the following reason. So now remember, initially I had the cis isomer in this form. So this is the cis isomer. So if I may put it back and show you how cis is a bit unstable compared to the trans isomer. So now remember we have this double bond. This double bond has a cloud of electrons around here, and on top of that we have these bonding molecular orbitals, or these covalent bonds that also have electrons, plus these other electrons around here. So we have a very big cloud of electrons on this upper part. And remember, electrons repel each other. So this a cis molecule is a bit unstable because of this too much electron cloud going on here. And this usually makes this molecule get what we call steric hindrance. Steric hindrance is when we have a lot of electrons in a given region of area, hence leading to instability of a compound. So cis isomers have what we call experience with what we call steric hindrance because of these too many electron clouds along this upper part of the molecule. Whereas in cis, we see that there is even distribution of these electron clouds. So therefore, if this methyl group is on opposite side with this, there will be less steric hindrance. Hence, the trans molecule is more stable than the cis isomer. So now that we've seen cis and trans, so what if, remember I said for something to qualify to be under cis and trans, it must have a hydrogen on both the sp2 carbons. So if this is my sp2 carbons, this carbon must have a hydrogen and this carbon must have a hydrogen to qualify for cis and trans isomers. Now, what if we do not have hydrogens on both? How can we name such compounds? So now, these scientists came up, or the chemists came up with another naming system of the E and Z system, whereby if so now if these sp2 carbons do not have a hydrogen on them, then we shall take the priority of the next compound on the compounds that they are bonded with. Now, for example, if I may modify my structure here, so if I could take off this these hydrogens and I replace them with the other different atoms, now if I have something like this, so I've taken off the hydrogens and I have different atoms. Let me say this is nitrogen and this is bromine. So I cannot name this as a cis and trans. So what I will do, I will use the E and Z system. So now, the E and Z system uses what we call high priority and low priority. So what makes a compound to have a higher priority or a low priority? So we are going to see some of the reasons how we can name according to low or high priority. So if I have, for example, if I have on the upper part, if I have low priorities on the same side, like we saw in cis, then high priorities on the same side, then that element or that compound will have what we call the Z isomer. So when, for the E isomer is when you have the high, the low priority. For example, if I have low and high on the same side, if I have something like this, low, high, high, low, then I'll have what we call a E isomer. So just to remember is that Z isomer means them, like same side. So if you have all priorities with high on the same side or low on the same side, that qualifies to be a Z. Whereas the E isomer is when you have low and high mixed up together. So to get the E isomer. So now, thank you very much for watching. In my next coming video, I'm going to elaborate more about the E and Z isomers. Thank you. Bye for now.